Welcome to lecture 30 on risk management and insurance. In this lecture, we have a second look at the put-call parity condition. Remember, we discussed the put-call parity condition already in the last chapter when we did the option pricing model of insurance. Now, equation 35 is a put-call parity condition. It relates the call option price of a share to the put option price on that share. The left side of the put call parity condition, you can think of being in a portfolio. We have one call option with a strike price X, and then we have a certain amount of cash. Actually, it's amount of the strike price discounted. So if the strike price is $50 on that call option, then you discount this by the interest rate over the time interval from small t to big T. So maybe then you have here $49 and something in cash. On top of it, you have the call option. And this must be equal to the put option, to the value of the put option, and the value of the underlying share. That would be portfolio B. Now, this put-call parity condition is again an arbitrage condition. If it's violated, you can make profits without any risks, and then the arbitrage condition again re-establishes itself. Now, this equation holds at time small t. It holds when this option is written, the call option. The call option is written at time small t, the put option is written at time small t, and then actually here we have the share price also here at the beginning of the interval. And here we have the strike price, which applies then to time big T, you see, to the expiration date, so we discount this here by the interest rate. So let's show why this equation must hold. Now at time big T, let's first look at time big T and then at time small t. Be careful what we do here. Because this equation holds for time small t when the options are written. Now let's move ahead and let's go to time big T when the option expires. At that time, most portfolios will have the same value. Actually, this here, the maximum of the share price at time big T or the strike price, whatever is bigger, that will be then the value of those both two portfolios. This we can quite easily show here. So portfolio A is a call option, and we have this cash discounted. So call option plus the cash discounted. And at time big T, the call option will be this here. You see, that's again the boundary condition, that's the endpoint condition. So at time big T, when the call option is in the money, then there is this positive payoff. So if at time big T, it turns out maybe the share price is 120, the strike price is 100. Okay, you have the holder of the call option has a right to buy at 100. That's a strike price. In the market, we have a price of 120. So there is a positive payoff here for the holder of the option of 20. Now, if the share price is only 80, then naturally the holder of the option will not exercise and will not buy at 100, and so just walk away. And so we have the 0. So we have the maximum of the two. That's just this endpoint condition of the option at time big T. And then we have this cash here. This cash from time small t to time big T just earns you interest. Now here we have it discounted. Now we have, when you now earn interest, so in the end you just have X. You see, you have X to the E minus R, and then you multiply with e to the r times the interval. So that cancels out, the two e's cancels out, and you just get the x. So here we have something like $49 and something, and then it earns interest, and in the end we have the $50, the x. So here we have the x. And then remember, this we are allowed to write into this expression with the maximum. So here the x cancels out, st minus x plus x. And here naturally you also have to do it 0 plus x. So 0 plus x gives me the x down here. And the st minus x plus x gives me the st. So at time big T, when the option expires, we have the maximum of those two. Same thing with the put option. Here we have the put option plus one share. The endpoint condition for the put option, this expression here, remember that from chapter 1. It's actually the maximum of x minus st or 0, if you are the holder of the put option. Again, you have either something positive or you walk away. The put option is the right to sell. So here it has turned around. Here it's s minus x, now here it's x minus s, because that's a put option. Look it up again in chapter 1. And then you have the st, one share. That's now at time big T. So this becomes a big T. And so we have here x minus st plus st, so I'm simply just getting an x. And here, if you put it into the bracket, you have 0 plus st, so I just have the st. So it's the same as here, the maximum of st and x, the maximum of st and x here. So the two portfolios are equivalent at time big T. And so they will be equivalent also at time small t. At time big T, you have the same, the portfolio are equivalent, so they must have the same value also at time small t when the options are written. So this argument establishes the put call parity condition. So it's quite a simple argument here, actually. Now, when you look it up on the website, here, this side, I still do a little bit more complicated. It's also correct what's on the course website, but I have changed today. I have changed actually the notation here, and okay, made it a bit simpler. It's an arbitrage condition. Let's assume the left side is less than the right side. Always with arbitrage, buy cheap, sell expensive. So here, buy a call option, write a share, sell a put option, write a put option, and sell one of the shares. Okay, maybe you don't have it, so short sell it. So that's on the left side, that's cheap, buy a call option. On the right side, that's expensive, sell a put option, which means write a put option, and short sell a share, or just sell it if you have it. This will produce you a certain profit. I don't go through the calculations. You will find it in the Hull books. They may do actually a numerical example. It's a bit tedious, and it would require me an entire lecture. So we'll look it up in the Hull book. Now, if it's the other way around, so the left side is bigger than the right side, now you sell a call option, you write it, you sell the call option, and you buy a put option because that's cheap, and you also buy one share. Now, if everybody buys put options and buys shares, this drives up the right side here. You see, we move toward equality. And selling here, so call option, writing it, this drives it down. So actually, those arbitrage condition have a tendency to establish them automatically. Okay, so numerical example you will find in the whole book, but it will take you maybe 10 minutes to work through it. So we have done up to now the call option. We know the Black-Scholes solution for the call option. Remember, that's this one. We know here from equation 29, we know the solution for the call option, the Black-Scholes solution of the call option. We also would like now to know the solution for the put option. Now we don't have to solve the differential equation for the put option. What we can use is actually directly put call parity. And then we get the price of the put option. So we begin here with the put call parity again. And we have the solution for C. That's equation 28. The Black-Scholes solution for the call option price. And then we just simply solve the put call parity condition for P. And then we will have the Black-Scholes solution for the put option price. And there is no need actually here to solve the differential equation. So let's now plug in 28 here. At 29. So I take 29 here for C, I substitute this in. So I substitute 29 in here. I rearrange. It's straightforward algebra. It's very easy. Straightforward algebra. I get the P. It's a bit messy, but straightforward algebra. And I solve it here for the P. And I do a bit of rearranging. And I introduce those brackets. I collect the terms. And I'm getting here 36 for the put option. Now it's usually not yet written down like this, like 36. 1 minus the cumulative distribution here, value of the cumulative distribution. I actually can write for this minus ND1. And you see it down here. So 1 minus ND1 is just N minus D1. You have here the area beneath, here's the cumulative distribution. So the distribution up to ND minus 1 gives me actually the part here on the left, all that stuff here. That's 1 minus ND1. So that stuff here. So that red stuff here, that's the value of the cumulative distribution up to DI or D1. It holds for D1 and D2, so I call it DI. And then because everything is symmetric, the blue areas are naturally equal. And so it's 1 minus ND1 is actually N minus D1. So this here, the blue area must be equal to that blue area, which goes up to minus D1 or D2. So I will now, instead of this here, I write now that here. So that makes it a bit easier. And then it's usually written down like this. So that's now the price of a European put option on a non-dividend stock in the Black-Scholes model. But we did not solve a differential equation here. We just simply used the solution for the call option, and then we put it into the put call parity condition and solved for the put option. Now here again you have sensitivities. You have all those partial derivatives. What happens now here when the interest rate changes? What happens here when the sigma changes? The volatility. T1 and T2 will change, and it will have an effect on the price of the put option. So you have actually here a lot of formulas. You have it also here for the put option. I only gave it to you for the call option. You see we have here the delta, we have here the gamma, we have the vega, the theta, the rho for the call option. Now you have now those expressions also for the put options. Naturally, you have now here different partial derivatives. You will find them in the HAL book. I don't go through it, it's too much repetition. But they will look different naturally than the ones for the call option. Now, what we did up to here, we did the European call option. Now, remember, the European call option can only be exercised at the end, at the expiry date. The American call option also can be exercised before the expiry date. And it turns out that the price of an American call option on a non-dividend paying stock is equal to that of a European one. It doesn't matter for a call option on a non-dividend paying stock. For a put option, there is actually no closed form solution for an American option, and you have to simulate it numerically. We will do a simulation in the third computer assignment. You will see how you can simulate option prices. And then everything changes again if you also consider dividends. That's also in the HAL book. And again, you have new sensitivities, you have new formulas, you have a lot of formulas here. But you can look it up in the HAL book if you need it. As I said before, we have done this already in chapter 3 with insurance. So we used, in the end, when we applied option pricing to the insurance company, we got the put-call parity condition. And for example, you could use it to determine the optimal capital structure of the insurance company, or by the way, of any other firm. So that was in chapter 3. So the put-call parity condition is something very convenient and something very important in finance. I have here an example. So let's have a share price of $52 today at time small t. The strike price, which applies to the end at time big T, when the option expires, let's say, assume that's $50, the share price. So we have an interest rate of 12%. We have a scaling factor for the standard deviation of the underlying geometric Brownian motion of the S variable. This standard deviation is just the volatility of the underlying share. Let's assume that 30%. And let's assume the option has an expiration date of 3 months. Options are usually quite short term, up to maybe 1 year. It would be difficult for you to find options with beyond 1 year, with expiration dates that exceed 1 year. So 3 months is quite usual, 6 months, maybe 9 months, maybe up to 1 year. So you plug everything in, you get the D1 and the D2. Just put it in. And then here you have the D1, that's what you need. And the D2, you need it to get the cumulative, the value of the cumulative distribution. So the D1, it's actually set, the D1 is here. And then that's this area is 70%. So that would be the cumulative, the value of the cumulative distribution, the 70.4%. You can get this out of a table, or maybe you get it out of R. Then you do that for D2. So 17.42%. And you plug it in here. You see here I have the 17.42. I have the share price at the beginning, 52. And here the X strike price is 50. Then the ND2 was 0.6504. You see that one was 0.6504. You plug in everything and you get $5. So the value of that option is $5.06. It's a call option. And here I show you just again, so you're absolutely sure what you have calculated. You see, you calculated this down here. So $5.06. That's what the buyer of the option has to pay at the beginning when the option is written, and or also when actually somebody then later on buys the option, then it will change over time. But so this option is just simply with those data has a value of $5.06. Here you have the strike price of 50. It's a call option. So that's how options are valued in the market. You can use this Black-Scholes model, but naturally the model is only correct if the parameters don't change. If this volatility parameter, particularly crucial is this volatility parameter, that one goes into the D1 and the D2. That's actually the single crucial parameter, the volatility of the underlying share price. It's assumed that that one is fixed, and this parameter, how we get that one, we will discuss in the next lecture. Thank you.